It has laser lab, it has nuclear lab and renewable energy lab. Upstairs whole floor was dealing with solar energy and this floor was dealing only with the laser lab. And downstairs we used to have big two accelerators, and one we call neutron generator and the other one was accelerator. And both machines are now down. We have a portable neutron generator downstairs. So this lab is still alhamdulillah open. And this was the big group at that time, professor from chemistry. This is Professor Abdulaziz Suyan, who was director, last rector here, then director in Abdul Batam. This is the founder who started Dr. Shale Laser. They all left, most of them. I am this one, you can see here, I came out to us, so I have my hair like this. And so many people now left this lab, but we are still struggling to keep this lab alive in lasers. Okay? So this is the history. We have developed some technology in collaboration with MIT, and we developed some material, nanomaterial now using lasers. Alright? I will explain you how we do that. And those material when we have with us, we can use for different applications. And one of the applications which we were doing with MIT, oil water separation. If you give me a mixture of oil and water, so we have some mesh of stainless steel. We coat that mesh with certain nanomaterials. That mesh acts completely a new material. It attract water but repel oil. And due to some, we generate on the surface some forces, force of repulsion and force of attraction. So for water, we generate very high force of attraction, that surface, and for oil, it repels that. So oil stays up, water goes through this mesh. So we can separate and all. You can ask me why we need this technology. Because this new, what US is dealing now are applying, because previously US was the importer of oil. Now it is exporter of oil, because they have developed new technology, what we call shale gas technology. So under the shale gas technology, they use a lot of steam and water to break the rocks. And from these rocks they can bring the oil out. When they do this, they generate a lot of water mixed with oil. And they say that they use 7 barrels of this water to generate 1 barrel of oil. So you can imagine how much oil and water which is contaminated they produce from this technology. So you need to develop some technique how we can separate this oil and water to clean this water and for reuse. I mean, in this country we throw away. I mean, we are also using nowadays, our oil wells are old, aged, so we need to pressurize them to bring oil out. I mean, a lot of water out. But we don't care for that water, we throw it away, whatever is mixed with after reuse. So the technology is well needed now to develop such surfaces or meshes or membranes we call, so that we can separate oil and water. Okay, so this was our main project, 5 years. Alhamdulillah, we have 5 or 6 patents already got on this technology. Still some, our patents are pending. We published in good high-profile journal like Nature Scientific Report or Applied Material and Interfaces, which is ACS journal, have impact factor 7 and like that. So through this project. And this project still we are continuing. Normally are very highly carcinogenic. Okay? Even 1 ppm of this mixture of these dyes in water, if you drink, nauzubillah, you get the cancer, okay? Straight away, and it can kill. So we use these materials, we call them as a catalyst, nano catalyst, and we put in a water, we shine the laser or the light or the sun even. we can excite these catalysts. They act like a semiconducting material. So as you know, maybe you have a course in semiconductor. Semiconducting material has a valence band and a conduction band. So if you shine the light, you tunnel one electron from valence band to conduction band. So you can produce electron-hole pair. And this electron-hole pair, when attacks the water, it breaks the water into hydrogen and oxygen radicals. I mean, they are charged species. And you have now OH radical and oxygen, atomic oxygen. Now this OH radical and atomic oxygen we can use for cancer treatment. We can kill the cancer cells if we like. We have some PhD thesis we done recently. You can use them to, these organic compound, these dyes which are mixed in water to break them. And you can get clean water from that. So that project we are also working on. This one same these nanocatalysts we can now use for, as a semiconducting material to develop solar cells. And these cells what we call dye-sensitized solar cells, okay? So what we use these, for example, these are mostly metal oxides, titanium, TiO2, ZnO, zinc oxide, or WO3, tungsten oxide, or iron oxide, and many more of this family of metal oxides, okay, which are semiconductor. So we can use them in dye-sensitized solar cells. We can use them even to make supercapacitor to store energy. So many things we can do. That we have a laser beam, and you all know laser is a very strong source of energy. When it interacts with the material, it can do many things. These electrons, with these photons which are coming from the laser, if their intensity is too high, or the power per unit area is too high, you can even drill the hole. Or you can do a welding with that, like a welding, this arc, okay? The charge what the guy used with acetylene gas
Yes.
to generate very high temperature, where gas, the metal can melt, and you can drill the hole, you can cut the metal, you can even weld the metal with each other. So, and that is what US was trying to destroy missiles, okay? And they have already built a laser system which can really destroy any target in the sea or wherever you like, okay? So we are just exposing you here just that we are using around 400 millijoule energy, and we focus this energy in on some material like zinc oxide. So if I have a zinc oxide bulk material which is micron size, now if I shine my laser, I can create plasma inside this material, or I can create very strong shock wave, and this shock wave can break this material which is bulk, yani micron size, into nano size. So that is, we call, laser generated shock to produce nanomaterial, or you can call it pulse laser ablation inside a liquid. We are not doing in solid but inside water. So we first put this material, for example, I have zinc oxide, but it is micron size. I need it nanoside or quantum dots. Quantum dots when material dimensions are less than 10 nanometer. Then we are reaching close to Bohr radius. You know what is Bohr theory? You have a proton, neutron in a nucleus. Outside you have electron. The lowest energy level electron, which is closer to the nucleus, that's we call we are close to the Bohr radius. So when such situation we arise by the laser, we can make quantum dots. And these material have one-dimensional, they don't have three-dimensional now because they are very, very small, orbit in which electron is moving. So we can make quantum dots with it. We can make, 50 nanometer size, 100 nanometer, less than 100 nanometer size for nanomaterials. Okay. So are we ready? You can see here the laser beam. Yeah. So this is 532 nanometer, which is basically second harmonic of 1064 nanometer. Okay. And we can also generate we have a crystal here. If I put third harmonic generation, I can make out of 1064 nanometer 355 nanometer. I have fourth generation also. I have crystal. I can make 266, which is ultraviolet. Okay, and we can do with this laser or this laser. So you see here. Can we raise the energy, please, so that they see some spark. So now he is raising energy, which is not good for our eyes. This is a shock wave being created. Although these are photons, can you increase a little more? Yeah, they like to listen to more. No, it's not going to them. They are young people. Now you see, this will burn the whole thing now. So this is a shock wave that photons are hitting and creating very big sound. Great?
Not the maximum.
Yeah, it's not yet maximum because we don't want to damage your eyes. So in this focus, we put water mixed with material which we like to make damage. Okay, through this shock wave which you are hearing, very strong wire, sound, right?
Yeah.
So this is the interaction of photon with that solid material. By why shock wave is created, how shock waves are created, you have some knowledge, Ali, and you are engineer.
This is a sound.
You can create a thermal gradient, a high temperature at the focal point. And when you have this, the material which is there or the air which is there, it goes away very strong. And from the surrounding, your temperature is 20 degree. While there, I am creating 10 to plus 4 degree Kelvin by this high temperature, by this focusing of laser beam. So the surrounding air goes into that place. And that's why this expansion, expansion is creating shock wave. Okay? And when you have atomic bomb, also the same principle it takes, and it creates a lot of sound. Because where it hits, a very high temperature is created, the surrounding air comes in, and you create a lot big shock wave which can destroy your even electrical installation or electronic installation. It can create even a nuclear pulse, they call. A very strong electrical pulse, which can, if AC is working, it will be damaged. If television is working, it will be damaged, because television cannot sustain 1 kilovolt or 3000 kilovolt pulse, or maybe 1 megavolt pulse. So that's, the nuclear shock waves are created. So we are creating shock waves to break them, these bulk material into nanosize like this. Okay, so here, so maybe I can show you how we shock wave. Here we create material, and this laser will produce pulses which are in ultraviolet region. Yani your eye cannot see. 266 nanometer. What is the range of our normal eye, my friend?
400 to 700 nanometer.
Huh?
450 to 400.
400 to 700. This is correct answer, mashallah. Good. Okay, now I'm starting this laser. And now you can see, although there is a very little green going up, but this light is going there. Okay, you can see here. It's no more green now, right? Yeah. It's ultraviolet. But ultraviolet our eye cannot see, then how are you seeing this? 266 our eye cannot see. My friend told our eye has a range 400 to 700. Why we are seeing? So it's basically not the light direct I'm seeing. It is the fluorescence produced by this paper. When ultraviolet is hitting, this producing this color which my eye can see. Okay? So, yeah. Okay, now what do we do here? For example, this is aluminium, or this is your Saudi coin, Saudi Riyal. This technique can tell me from which element this Saudi coin is made. Is there how much aluminium inside, how much copper inside, how much brass inside, how much steel inside, and things. So I can study elemental analysis through this technology. I'm creating now plasma here, and I have this fiber. Through this fiber I can pick up the light, and this light go to this spectrometer. Inside spectrometer there's a dispersion element like grating. This grating can disperse the spectrum into different colors or different wavelengths. So those wavelengths are fingerprint wavelength of each material which is present inside. You got it? Okay. We can turn off. So thank you very much. So this is called laser-induced breakdown spectroscopy, LIBS. Okay? Yani we are creating a plasma here. This plasma is emitting light. That light is characteristic of different element موجود inside this coin. Okay? We are using this technology now in many, analysis of many products, like cosmetic products which women use, lipstick for example, or the powder, or the eyeliner, or anything. Recently we have produced a thesis, the fish what we sell in the market here. 20 kinds of fishes are there which we sell. We were interested to know whether this fish can cause cancer if it contains mercury, or chromium, or cadmium, which are very toxic elements. So we just finished a thesis, we are writing a paper, we found some fish kinds which really contain some mercury also. It's not that we are bluffing. So we found mercury in them. Recently also we published one paper, we have a lady student doing PhD with us from the Mom University, and we study the nails of different people of different ages, and we found some correlation that some people who have osteoporosis, yani they have less calcium in their bone, they can develop this technique, so we can detect a correlation between calcium and their old age, for example. Young people have more calcium, old people have less calcium. So we can study this with this. Recently we have other project which we are also partially collaborating with Chicago University. Okay? That people have a colon cancer which is very common in USA, Nauzubillah. Not much because their eating habits are different than our habits, okay? So is there any correlation that people get colon cancer due to accumulation of heavy metals like zinc, barium, okay, and other these kind of metals, okay? So we are bringing, people who have developed colon cancer here and some healthy people. We are working with a surgeon and teaching hospital. Bring that, can we apply this technique on, because the beauty of this technique is within 2-3 minutes we can judge. They absorb moisture. Okay? Like these perovskite solar cell, if I make them here inside this room, they are not stable. Okay? For that we need this, there is a certain environment, high pressure inside of argon gas. There's no moisture, no water, nothing. So we put our hand, we put those material on this, heating, or when we measure this, we can weigh those material so that under that controlled environment. So that's the purpose of this glove box, to use them. We have this furnace, we can heat these material, calcination we can do to get rid of water, get rid of other impurities at 800 degree or something, okay, whenever we make material. Once we have this material, we can use this, this is called Autolab, the device, okay? Autolab. It can do electrovoltometry, what we call, and it can also study current versus voltage characteristics of these solar cell to calculate the efficiency and other parameter. Okay, it can also measure the impedance of that solar cell. Okay, we can use this device for that purpose. Okay? And of course we have when we have to do anything we can. This is a sonicator, so we like to make something, or we use this sonicator, this small device. So this Eczema laser is basically built on that principle that we mix argon and fluorine gas. Fluorine is also F2, it's a stable gas, it doesn't need any electron. Also argon doesn't need electron. But when we put these two gases in a high electrical discharge, we have two electrodes and we apply a very short pulse, nanosecond pulse on these two electrodes, around 28 kilovolt pulse, electrical pulse. Then this material, the gas which is in between, there is discharge created between that because every gas has a certain breakdown voltage maybe. How much is, by the way, you are electrical engineer, for air breakdown for
about
1 centimeter gap?
2,000 or 20,000?
2,000 is very little, Maulana.
20,000.
21 kilovolt.
Yes.
21 kilovolt is normal breakdown for if you have a gap of 1 centimeter. For nitrogen, it is less. For helium, it's maybe 12 kilovolt. Okay. But so when we have this 28 kilovolt, we have a breakdown in the gas, so discharge is created. This discharge, you have a lot of now electrons, they excite actually argon and fluorine, and argon and fluorine, they become as one molecule, which is only exist in excited state. When it comes down, is again argon is neutral, fluorine is again back neutral and stable. But due to this discharge, we have excited state argon fluorine, but no more ground state. So for any laser, what are the conditions, by the way? You have course in lasers or no?
No.
What are three major conditions to create laser beam? Population inversion. In the upper level, number of molecule in upper level should be larger than in the ground state. Under thermal condition, upper level has less than the ground state or lower level because it's a Boltzmann distribution. N2 is equal to N1 e to the minus delta E over K BT. Maybe you know this equation somewhere, okay? And so we create opposite to create a laser, okay? So that's done through this discharge and by short pulse. So that's why we call Eczema laser. The beauty of this Eczema laser is the beam is almost 2 inch by 1 inch. While there you saw a very small beam. So that's why this laser can be used for many industrial applications. And what the application, what we are doing here is we use same technique what we are using for ablation, but here we make films. Okay, we have target, we focus this beam, we ablate this material and remove this material, and on the other side we have a substrate, so we collect that material on the substrate. So now let's say I have a target of zinc and I put some oxygen gas in my chamber, in that chamber where I have a 10 to minus 7 vacuum. I introduce very little oxygen, so I can make a film of zinc oxide, Zn plus oxygen. From oxygen I break oxygen O2 into atomic oxygen. This atomic oxygen is very reactive. So when very small particle of zinc are coming through by ablation, they catch oxygen, make ZNO on the substrate. So I can make many material like this, very clean. And this technique we call pulse laser deposition. There we were using pulse laser ablation in liquids to make nano. Here we are making films with laser, okay, by ablation and combining with oxygen. Okay.
What is the name of the technique?
PLD, pulse laser deposition. Okay. So in this chamber, we can really make a very fine 10 nanometer thickness film, 20 nanometer, so we call thin film. And these thin films have very clean, very good properties. You can use them as a detector or sensors or many applications you can use them. Even you can use them. So now we have a PhD thesis. We are using this some films to make a thermoelectric effect. Yani thermoelectric effect is that if you make a little heat, you can generate electricity.
Yeah, it's
Or you can do opposite also.
this is the
You can
Seebeck
apply
effect.
electricity and you can generate heat. Or you can cool that thing. So Peltier effect, maybe you have read somewhere. So we are working on actually with the Renewable Energy Center to make some materials because in Saudi Arabia the solar cell has a big problem. At 2 o'clock you have a very high temperature here, peak 42, 47 degree. So the efficiency of the silicon solar cell, which is normally maybe 15%, it goes to 3%, 4%. So you need to cool them. And cooling is not easy in desert or in that environment. You need a lot of water if you use. We have already less water. We produce through desalination, right? It's very expensive water. So we are thinking this technology, if we can make this film at the back of this silicon solar cell, maybe we succeed to lower at least 10 degree temperature. Then efficiency will stay as it is. So this is called thermoelectric effect. We are working on PhD thesis. Okay, here we make those surfaces which we talked about, oil-water separation, and we use a very pressurized gun. We have a very fine gun of, let's say, a few micron size. We put it here, we put pressure, and we put this material which we like to coat on those substrates here on this, and then we can put a substrate and make a film as good as possible to use that for oil-water separation. And this separation actually we study through two properties, what we call hydrophobic, hydrophilic. Oleophobic, oleophilic. Anything philic means loves water. Anything phobic means is afraid, so it repels water. So we coat these surfaces on a very fine mesh, and this mesh is stainless steel, and the pore size is very small, 5 micrometer, very small, which you can only see maybe with some good scanning electron microscope. Once we have this, so we have to study this now, the what we call it contact angle. Any angle what water makes with it, and the angle what oil makes it. If the angle is below 90 degree, this contact angle, we call philic, yani hydrophilic. If this angle is above 90, we call hydrophobic. But if we exceed angle 150 degree, we call super hydrophobic. So we have made material here, mashallah, that can also go to even 160 degree. So they are super hydrophobic, okay? Or we can bring the angle from 90 to 0. They are super hydrophilic, okay? So to study that, we have this device here which we call goniometer. This goniometer is an optical device. It can tell you exact angle. So we put the water droplet here through this syringe here, and we shine the light here, and there is a telescope. This telescope, the ball, the water really, droplet looks like a ball. When, if I throw a ball, it will come back, okay? So if it is hydrophilic, this will wet, and we will not see this ball at all. It will just level on the surface. But if it is hydrophobic, it's like a ball comes back. So we have videos, we can, where you can clearly see that it is super hydrophobic or similarly super oleophobic or super oleophilic. We have this turning mirror which turn the beam 90 degrees. So beam is coming from there. You can see our all optics here is big. Their optics was very small because laser beam was just 6 millimeter. Here laser beam is almost 2 inch by 1 inch. So we need big 2-inch optics here. Okay? That's why this turning mirror is too big, the lens is too big. Even we put aperture ourselves, we made aperture to make it very clean. The beam, which is Gaussian, you can say, from the middle, so the maximum intensity of the beam is there. So the beam comes through this, we focus, and we put the target here. And target is rotating all the time. We can, in one time, we can upload 6 targets. I mean, for example, we can put zinc, we can put titanium, we can put copper, we can put silver, all this, okay, 6. And they are rotating continuously. And on this side, we have the substrate on which we want to make the film. It is around 2-inch distance, roughly, okay. And in between, we have a vacuum pump here. You can see this pump. There is one also inside what's called a centrifugal pump also. Very good one. So these 2 pumps can create a pressure inside 10 to minus 7, meaning high vacuum, so that no impurities or any contamination come into the chamber. Our film is very clean. It's pure zinc oxide. And then we introduce through these cylinders the gas and oxygen or hydrogen or whatever we like, I mean, film. Like if we want zinc hydride, we add hydrogen. If we like zinc oxide, we can put zinc oxide. If we like zinc nitrate, we can put maybe and oxygen. So like this, okay? So all this we can add. The beauty of this is that this substrate we can heat also to 800 degree, okay? So that, I mean, as the film is being made, it is calcined very clean also by heater, okay? So we can do that in this kind of chamber. It's almost 600,000 real piece, okay? With full negotiation, although it cost 800,000, but we have less, so we negotiated with the company a lot, and finally we got this in this. So these thin films are very important. I mean, you can have many applications of them. You can make sensors out of them. You can make these dye-sensitized solar cell. You can use as a detector, you detect the laser light or other detectors. So many applications of these thin films are nowadays in the market, which you can use them. I mean, you can make, I mean, thermoelectric effect or other many effects.
Where does the laser come from? Where does the laser come out from?
The laser come from that. That's actually, can you open this is a shutter. This, can you, it will open like this, yeah. The laser comes through that. Okay. That's a quite big beam. It's Eczema laser. There are four, 5 such system. 2 or 3 are only in cost because it's expensive. Laser itself costs around 700,000 also. There is one in South, one in Cax, one we have here. So not many units are available in the kingdom. Basically, 6-7 units are. Okay, this is another technique which we call ion plate, and you have again substrate like there. And now you apply high voltage between them. Okay. Due to that high voltage, you basically, I mean, suck out or you can pull out some ions, okay? And those ions then is basically material. On the other side you have negative, on side you have positive, so they will come with very high speed and stick with the substrate. Okay?
This is basically ion implantation.
Yes, ion, not implantation but sputtering. You sputter those things. Okay, and sometimes people use if you have a neutral, you can use magnetic field to sputter these ions. And the magnetic ion sputtering units are also available in the market. But main purpose of this is again to make films, like we make there. There we can have much better and clean control with laser. But here also you can do that. But there are some drawbacks that some material. Like for example, if you want a film of plastic, which is a neutral material, it's not possible like this, because okay, but there it is possible. So there is thermal. We bubble this gas in this cell. We put our catalyst inside, and we shine the light. This light could be laser. This light could be a lamp. this light could be a sun. Okay? To excite this catalyst semiconductor material. Once we put this carbon dioxide and water, we can make methanol, which is high value hydrocarbon, and it's called green fuel. Okay? So once we do this, we have to monitor that whether we made some methanol or not. So we need this GC gas chromatograph mass spectrometer. This okay? And we have finished this project recently. That's why we are not operating now this, but we are writing another proposal now to make a new catalyst which can give us better efficiency of conversion. So the big hurdle in this is how we can go at high efficiency but at room temperature and ambient condition at atmospheric pressure. Okay? Present technology which converts CO2 works at 800 degrees and pressure of maybe 80 bars, 80 atmospheric pressure. Okay? So we want to develop something which is cheap, which works at ambient condition like room temperature and room pressure. So that's what our purpose. Okay? So with that's mostly our projects which we are running.
Is this the energy storage element?
No, that Maulana already showed. Did not mean that he's. But why? What is capacitor purpose? What is the purpose of resistor? What resistor does?
It limits the current.
Consume
It can.
the electromagnetic
Save that.
electrical field is
Okay.
stored.
Both has to do with charge. Let me give you the hint.
Yeah.
Okay? Both have to do with the charge. So what is the difference between resistor for a charge? What is the purpose? The capacitor does.
The electrical field of the capacitor.
Dissipation of charges. That's fine.
Uh-huh.
Capacitor store the charge and you can use anywhere you like. For example, Nauzubillah, if somebody has a heart attack, when they take him to the hospital, what they do first?
Give him.
They give him a shock. They put 2 electrodes and charge a capacitor and discharge this very fast on his to give the shock. Correct? So that means capacitor is used to store the charge. And flow of electron or the flow rate is controlled by resistor. Okay? So that's the difference. Yani current is dq by dt. Charge, how much flow in how much time. That you can control with resistor, my friend. But if you need a charge for a certain purpose, you can store it with the capacitor. Energy come after. Energy you can say also, but that's now we use this word because everybody is talking renewable energy. So energy storage is important. So supercapacitor is 20 times more capacitance than normal capacitor, but its principle is quite different. It doesn't have electrode, but it does not use the dielectric material. Rather, it uses some electrolyte, and these 2 electrode and electrolyte, they have some chemical reaction. They produce radicals, and these radicals are separate. On one side is a negative radical, another side is your ions. Okay? So these material, that's why the surface area is too large. So the basic formula of this is epsilon naught A over D. So this epsilon A over D is the capacitance. So this surface area you can control by these porous material or nanomaterial, and the D is very small because the charges are just separated very small at a micron region level. So you have super capacitance, big capacitance on 20 times more. So that we are working also to make super capacitor by these material. But we didn't discuss in that lab because this project we just started.
Why would someone use a supercapacitor in such a
That's really a very $1 million question again.
Fast discharge.
Because during day you have solar energy, In night you have no sun. Now what you do during night, Maulana? Because if you have to run your computer, you have to run some devices, you need again electricity. So you have to store the electricity. So that's the purpose of it. And you can use them very fast switching. But these are better devices because you can switch the electricity very fast with these capacitors, which is not possible by battery. For example, you have to put brakes on your train, electric train, or put brakes on your bus. So such capacitors we charge and you can use quickly and use them fast in this application. Or in some medical application where switching is needed very fast. So they are ideal for these capacitors.
But I mean, they're not used for mass storage of energy.
They will be one day. That's the ultimate aim and goal. But switching of, charge or switching of these electricity at a very fast, let's say nanosecond or picosecond or femtosecond or even, let's say, microsecond. These are ideal. Batteries you cannot charge very quickly. Okay? Battery has certain, internal resistance. Correct? Yeah, you have, they are teaching you and we teach in our physics. Internal resistance is roughly less than 2 ohms. So the path length is also very small for these supercapacitors. Yes.
I have a question. You talked about previously about using the heat and the coldness to generate voltage.
Yeah.
You're talking about
Thermoelectric effect we call it.
it's a Peltier effect.
Many heat, generation of heat by electricity or generation of electricity by heat. That
This
is
is-
what the word means, yeah.
It is called Seebeck effect. And
Yeah, exactly, Seebeck effect, mashallah. You reach to the right place, yeah.
There's the other one that uses heat cooling.
Peltier.
Peltier.
Peltier effect. It is opposite to that.
Yeah.
Yani you apply small voltage, you take the heat out. Otherwise, you put heat, you generate electron.
This
Both
is
work
being
out.
used by NASA to power the Mars rover and
Yes. We are dreaming also here, NASA, yeah. We make these thermoelectric coatings and use them. A dream we can do, right? No money, it doesn't cost. Okay, please ask if you have any other doubts or questions regarding what you have seen here. You are welcome.